at infinity. So we had the several limits here. So we use L'Hopital's rule for infinity over infinity and 0 over 0. There are other indeterminate cases in which we can use L'Hopital's rule, and let's see which ones we encounter. So there are 7 indeterminate forms. If the book says forms, let's use forms. That's fine. So we already seen these. And there are 4 more to look at. We're going to add 4 more in a minute. I would like to look at a problem, and we're going to come back and add the other 4 in as we encounter them. So here's a limit as x approaches 0 from the right, from sine x times natural log x. Okay, so we're asked to find this limit. First, I have to plug it in and see what's going on here. So sine approaches 0 as x approaches 0 from the right. And remember the graph of natural log. Here's the graph of natural log. So this approaches negative infinity for 0 from the right. This is natural log. And you can say, oh, it's very simple. 0 times negative infinity is 0. No. 0 times infinity may or may not be 0. We don't know that. So what should I do next? And the answer is, what I am going to do next is try to change this into L'Hopital's rule so I can continue using L'Hopital's rule, because with 0 times infinity, I cannot use L'Hopital's rule. So the question is, what do I do? Well, a simple algebraic manipulation. I will not touch log, but I will change sign without changing the function. And bringing it to the denominator is 1 over sine x. So remember, these are 2 fractions, natural log x over 1 times 1 over sine x, and I have to flip 1 over sine x. Right? And I get the same thing. But I do know that 1 over sine x is basically cosecant. So I will continue here. So this is limit as x approaches 0 from the right, from natural log over cosecant x. 1 over sine x is the same with cosecant x. Now I check again. The numerator approaches infinity, or negative infinity if you want, it's the same thing. But now 1 over 0 from the right will be infinity. Yay! Why am I happy? I'm happy because I changed the indeterminate case 0 times infinity into an indeterminate case or form in which I can apply L'Hopital's rule. So remember, L'Hopital's rule is applied only inside a limit. If I don't have a limit, I cannot discuss or apply L'Hopital's rule. So I will copy limit as x approaches 0 from the right. I'm checking my computer battery. It's okay. And I differentiate the top, and I get 1 over x. And now I differentiate the denominator, and it's negative cosecant cotangent x. Now I will check again and see what's happening here. Before I do that, I would like to see what this product really means. So on the side, I would perform a calculation. Cosecant is 1 over sine x. Cotangent is cosine over sine. So I want to change this into this, which is negative cosine over sine squared. I come back to my calculations here, to my limit. So I have limit as x approaches 0 from the right. The top is 1 over x, and the denominator is negative cosine over sine squared. I will divide the two fractions. So I have negative 1 over x times, I flip, sine squared x over cosine x. And now I know that when x approaches 0 from the right or left, it doesn't matter for cosine, this will approach 1. I also know that the limit of sine x over x when x approaches 0 will be 1, but only one of them, right? So let me rewrite it so you understand what I'm trying to do. I will rearrange it. I will keep everything but rearrange so I can explain better. So limit as x approaches 0 from the right. Of course, I should put brackets or parentheses because I have that negative symbol. So 1 over x sine x times sine x over cosine x. So what I'm really saying is this. When x approaches 0 from the right, this approaches 1. We already know that this also approaches 1. We talked about that limit many times, and we know that the limit of sine x over x when x approaches 0 is 1. And what am I left with? This is gone. This is gone. So I have 0 from the right. Sine x is 0. 0 times negative 1 is 0. However, this is by chance. We can never assume that 0 times infinity is 0. By chance, we got 0. But please do not ever assume and conclude. If you get 0 and infinity, you can say that this is 0. You cannot say. It's an indeterminate form. The answer can be anything. It happened to be 0. Okay? So that was another example. The most involving ones are something like this. Let's say limit as x approaches infinity from e to x plus x raised to 1 over x. So the power ones.
I have a question.
Yes,
for the
please,
previous
please.
one.
Yes, please.
So when you turn sine into what was it? It was like cosecant, and then it would turn into infinity over infinity. I'm confused. So cosecant, if you plug in 0, cosecant would turn into infinity.
Because it's 1 over 0.
Okay.
1 over 0 is cosecant. So this is 0 from the right. So 1 over 0 from the right is 1 over x. So when I graph this 1 over 0, it's basically this function. So it's approaching infinity.
Okay.
So this approaches infinity.
Okay, got it.
I named it better cosecant so I can differentiate it easier, but it doesn't matter. You don't have to consider that. You can just write sine to negative 1 and you will get this probably from the beginning. So you don't, I just wanted to show, you know, and work with cosecant, but you don't have to. You can apply the chain rule on this as sine to negative 1. And then you will not have any cosecant. Is that better? Did I answer your question?
Yes.
Okay,
Yeah.
perfect. Okay, so as you see, these are the ratios. So we found a product so far. And this is a difference. And we have 3 more to discuss. The powers are the most difficult ones. And this is a power. So infinity. So infinity plus infinity, this is infinity. 1 over infinity is 0. So infinity raised to 0 is the next indeterminate form, and it's a power. Okay? So this requires more work than anything else, the power ones. Like before, what reminds you of a power, a function raised to a function? What does it remind you of?
Chain rule.
True,
Or
but what did we apply for the chain to get to the chain rule?
was it taking the natural
Yes,
log?
yes. Thank you very much. Indeed. I have no choice. I have to bring 1 over x down, and only natural log does that. So first, I denoted this. So step number 1. This has many steps, and I'd like to clarify them. So step number 1, I have to name the function by y. In step number 2, I apply natural log to both sides. In step number 3, I apply the limit here to both sides. And you could say, wait a minute. You're not asked to find limit of natural log. That's true. I'm asked to find limit of the function, not limit of the natural log. But you have to bear with me and allow me to apply limit as x approaches infinity, because that's what I have, to natural log y on this side, and I have to apply it to this side. Limit as x approaches infinity from natural log e to the x plus x over x. So in a roundabout way, I will determine the limit of the natural log first. I'm happy, very happy, because the top goes to infinity, the bottom goes to infinity. Yay! I can apply L'Hopital's rule. No headache on this one at this stage. So I have 1 over e to the x plus x times the inner function prime e to the x plus 1. Yay, the denominator is 1. I love that. So now I rewrite as limit as x approaches infinity, e to the x plus 1 over e to the x plus x. No problem. This is still infinity over infinity. I can do infinity over infinity as many times as possible. I don't care. L'Hopital's rule is so good to me, to us, if you want. So limit as x approaches infinity, I differentiate the top, I get e to the x. I differentiate the denominator, I get e to the x plus 1. Okay, I differentiate again. 1 will go to 0 when I differentiate it, and I get 1. Very nice. In step 4, I copy the beginning and I copy the end. Just that. So I have limit natural log y when x approaches infinity is 1. And now, a long time ago, in chapter 2, there was a theorem that allowed us to swap the operators. Operators under the conditions of continuity. Yes, everything is continuous. E to the x plus x to 1 over x is continuous. Okay, so then I am going to swap the operators. So I swap the operators. Natural log of the limit as x approaches infinity from y is 1. But I know a very important rule that allows me to change log base a of x equals y into its equivalent exponential equation, a raised to y equals x. Very important from algebra. Any log equation can be replaced by an exponential. Any exponential can be replaced by its corresponding log. So what is the base here? The base of natural log is?
E.
Good. So e to the first power is our limit. So therefore limit e to the x plus x to 1 over x as x approaches infinity is e. But yes, they require a lot of work. A lot of work. And we can look at another, if that's what you like, of this power. And we have two more powers. We had infinity raised to 0, and we have two more powers. I want to add them here so I don't forget. 0 raised to 0 and 1 raised to infinity. So 3 powers, 1 product, 1 difference, 2 ratios. 2 ratios, 1 difference, 1 product, and 3 powers. These are the most difficult ones because they require log and a lot of steps. Would you like to look at another power?
Yes.
Okay. Okay. 15. Here it is. Limit as x approaches 0 from the right, from tangent to x raised to x. I plug it in, tangent at 0 is 0, and this is 0. So this is our second power. We had an example of infinity raised to 0, and this is another example now of 0 raised to 0. And no, you cannot conclude is 1. No. It's an indeterminate form, no conclusion. We have to work this through step by step.